Welcome to one more web note on this time properties of functions defined on metric spaces or between metric spaces. As we said all the time, the idea here is to inspire ourselves of the real line, the set R. So basically, most of the definitions are exactly a mirror image of functions or properties of functions defined on the real line. Of course, there are properties that are proper to the real line that may not be able we may not be able to extend these properties to the general case of metric spaces. But the spirit, the definitions, many properties are already in the real line, coming from the study of functions on the real line. So a very good knowledge of the real analysis course with a good knowledge on functions, real valued functions, will really help see these extensions to metric spaces. So first of all, we need here, of course, because function will be defined on a starting set and an end set, and therefore both the starting set and the end set, or the set of inputs and outputs, are both metric spaces, and in general they don't have to be the same. So here we will assume in the framework will be the framework throughout all these web nodes. It will be MD, the set of inputs, and N row are two matrix spaces. F goes from M into N, will be called a function. And most of the time, we'll assume that in fact F is not defined on the entire set M, but only on a subset D into N. And D will stand for the domain of the function F inside the set M, the metric space M. So again, sometimes I will mention the distance D and row, but sometimes I will omit them. But keep in mind that D will be the distance on the starting set, and the row will be the distance on the end set or the set of outputs or images. As we defined in the real case the limit, let us also in this case define the limit. So we'll say, we will write in fact L equal limit f of x when x goes to a, if and only if for every epsilon positive there exists delta positive, such that for every x in D, the distance from x to a less than delta implies that rho, or the distance from f of x to L, less than epsilon. Let us make some little general comments here. Number one, we do not assume that x is equal to a. Therefore, here we don't need, but we need to have x close enough to a in D, and therefore, in general, we'll assume that a is a limit point of D, or an accumulation point of D. Okay? Here, using the properties of the distance, we can easily show that if L exists, if the limit exists, then it is unique. So we can talk about the limit of the function f when x goes to a. So sometimes we may write that we may write f of x goes to L as x goes to A. As we did in the real line, we are still as an extension the same theorem, beautiful theorem, which is sequential characterization of the limit. So we have this beautiful theorem. So let f d A as above, as we defined them above, meaning that f is defined from d to n. And we have limit of f of x equal to L when x goes to A, if and only if for any sequence xn in D such that limit of xn is equal to A, then limit of f of xn exists and is equal to L. So this is a sequential characterization of the limit using sequences for a function defined on matrix spaces. The proof is exactly identical to the case of the real line and will be omitted. A student can look for any course on real analysis or real variable functions and will find this proof. It's a beautiful proof and it follows exactly the case of the real line. Let us make a little remark here. We may, in fact, drop the condition, so we can say that limit of f of x when x goes to A exists. There is a limit if and only if for any sequence xn in D such that limit of xn equals to A when n goes to infinity, then the sequence f of xn is convergent. And if we assume that the target set n is complete, moreover, if we assume n row is complete, then in this case, instead of f of xn convergent, we can only assume Cauchy. F of xn is Cauchy. In other words, in the case of complete, we know that convergent is equivalent to Cauchy, and therefore, and as I said earlier in a prior web note, the advantage of Cauchy, it doesn't have to exhibit the limit. It's only a property satisfied by the sequence itself. So if the sequence itself is Cauchy, then we know it's convergent. And this, because when we claim that f of xn is convergent, then we have to have an idea of the limit and prove that f of xn converges to that limit. Let me just focus on the first part. Why we dropped L, okay? So first of all, what you want to show is that this condition here implies that the sequence f of xn has a limit and the limit is independent of xn. And to see this, indeed, okay, let xn and yn be two sequences in D such that limit of xn equal limit of yn equal to a. Then in this case, okay, we know that both f of xn and f of yn are convergent. So in this case, what we can do, so are convergent, and what we can do is to prove that the limit of f of xn is exactly the limit of yn. And to do that, we introduce a new sequence zn equal to xn over 2 if n is even, and yn minus 1 over 2 if n is odd. Yn plus 1, sorry. And this way, in other words, the Zn is, so for example, Z1 is going to be Y1, and Z2 is going to be X1. So we go Y1, X1, Y2, X2, Y3, X3, etc., etc. So the sequence Zn, okay, the sequence Zn converges to A. Okay, this is straightforward, same as for the real case, and therefore f of Zn is convergent. So since f of Zn is convergent, we'll see that f of xn is a subsequence of f of Zn. So both f of xn and f of yn are subsequences of f of Zn. Therefore, they both converge, and they converge to the same limits. So both sequences, subsequences, converge to the same limit. Once we define the concept of limit and the properties of the limit, and as we see here, this beautiful characterization of the existence of a limit using sequences, next we move to the property of some special functions where the limit is exactly the value of the function at the point. And this is, of course, brings us to the concept of continuity. Okay, so f defined from d subset of m into n, and a obviously is going to be in m, but in this case we have to be in the domain, otherwise we'll not be able to say that the limit is equal to f of a. Then f is said to be continuous at a if and only if limit of f of x when x goes to a equals f of a. So for us to have that f of a, it means that a belongs to the domain. So this is the definition of continuity as we defined it before. And now if we translate the sequential characterization we have for the limit into this setting, we'll get the following theorem, which is a characterization basically of continuity. F is continuous at a if and only if for any sequence xn which converges to a, we have f of xn converges to f of a. So this is the characterization, sequential characterization of the continuity of a function. So this is exactly, as you can, if you follow it carefully, we are still stating result that we have learned on the real line, in the metric setting. So nothing is changed so far. We have a new definition, which definition, okay? Let f goes from D inside M into N, okay? F is said to be continuous on D, is said to be continuous on D if and only if f is continuous at any point in D. So this way we have a global definition because the original definition of continuity is local at certain point, and now we have a global definition of continuity on the entire set. We know, so now what we're going to see next is to discuss the behavior of continuous functions on a big set with respect to the natural topology on the metric set. So first of all, as we learned in the real case, it's clear that the image of a closed set or open set may not be open or may not be closed, and we have an example, I mean, that you can see in any real analysis course. Take f defined from R into R with defined by f of x equals arctangent of x squared. Then f of R is 0 pi over 2. So as you can see, R being closed, the image is not a closed subset of R, and R being open, the image in this case is not an open subset of R. So the image of an open or closed set may not be open and may not be closed. Okay? But what we have, in fact, is a different property. I mean, this is, of course, the topological characterizations of the continuity. So here, theorem. So we have the following result. Theorem. Let f be defined from M into N. The following statements are equivalent. Number one, f is continuous on M. 2, for any open subsets O of N of the target set, okay, the inverse image F inverse of O is an open subset of N. Okay? Proof. Okay? Assume one is true. Okay? And let us prove 2 is true. Okay? Let O be an open subset of N. So we need to prove that that F inverse of 10. Let us prove F inverse of O is open in M. Okay, so we are going to show that every point in this set is an interior point. So let A belongs to F inverse of O. Okay, since F is continuous from 1 on the entire set M, it's also continuous set A. Then for any epsilon, there exists delta such that the distance from X to A less than delta implies the distance implies rho f of X to f of A less than epsilon. So that's just the definition of continuity at the point. Now, since A belongs to F inverse of O, then f of A belongs to O. We assume that O is open. Since O is open, there exists epsilon positive such that the open ball centered in f of A with radius epsilon is in O. Now we use the definition of continuity. There exists delta associated to that epsilon, okay, such that whenever d of xa less than delta, we will get rho of f of x, f of A less than epsilon. Now, what does it mean? It means that the the image of the open ball centered in A with radius delta is in the open ball centered in f of x with radius epsilon. Or f from our assumption is in O because the open ball centered at f of x with radius epsilon is inside O. Or equivalently, the open ball is in F inverse of O. So F inverse of O has A as an interior point. This shows that the inverse is open. So this finishes the proof that if we have 1 true, then 2 is true. Now, let us prove the converse. Let us prove the converse. Assume 2 is true. Let us prove 1 is true. Okay? In other words, let us prove that f is continuous on M. So let A belongs to M, and let us prove that f is continuous at A. Okay, so let epsilon be positive. Okay, so we need to find delta, and for that what we'll do, we'll consider the ball. So the open ball centered at A with radius epsilon is open in N. Now we use the property number 2. Using 2, we know that F inverse of this ball is open in M. Clearly, A is in F inverse of f of A. Okay, so there exists, because it is open, there exists delta positive such that the open ball is in F inverse of the open ball centered at F of A epsilon. Okay, it is easy to check that this delta works in the definition. In other words, okay, it is easy to check that whenever the distance from x to a is less than delta, we will get this row of f of x, f of a less than epsilon, and that's the definition of continuous. So f is continuous everywhere at any point, therefore it's everywhere. The f is continuous on the entire set. Remark. So the proof is over. Remark. So this theorem is stated in terms of open sets. What about closed sets? And for that, it's enough to see that, in fact, the complement, since f inverse of A complement is exactly f inverse of A complement. Okay? And once we have proven this identity, then one can replace, so we can replace in the theorem above, we can replace open by closed. So as we can see, function will be continuous if and only if on the entire set M it will be continuous if and only if the inverse image of a closed set is closed. So for the open and closed sets, it is the inverse image that is preserved by a continuous function and characterizes continuity of function. This is we call it the topological characterization of continuity. The case of direct image, in fact, as we did on the real line, in fact, we have a beautiful result. The case of compact sets. So now, compact metric sets. So in the case of compact metric sets, then we have some beautiful result. The first one is theorem. So what was not true for closed and open set is true for compact sets. That let f be from M into N, continuous. Let K be in M be a non-empty compact subset, non-empty compact subset M. Then f of k is compact. So the image of a compact set is compact. And the way to prove this, we can use the open covers. In other words, this result can be extended to the topological spaces. But in this case, in the metric setting, the proof is very nice and very quick using the sequential characterization of compact subsets. Okay, so here proof. Okay, it's enough to prove that f of k is sequentially compact. For that, let yn be a sequence in f of k. We need to prove that yn has a conversion subsequence. We need to prove that yn has a convergent subsequence with the limit in f of k. Okay, so now we use the definition of f of k. There exists xn in k such that f of xn equal yn. And now we use the fact that k is compact, since k is compact, there exists a subsequence xnk, okay, a subsequence of xn which converges to some a in k. Now, since f is continuous, it is also continuous at a. Since f is continuous everywhere, okay, on M, it is continuous at A. Okay, so f, if we look at the characterization of continuity using sequences, then f of x and k converges to f of a, which belongs to f of k. Okay, in other words, or y n k converges to f of a, which belongs to f of k. Therefore, we found a subsequence which converges to a point in f of k. The next result discuss another beautiful property, which is the min and the max of a function, a real valued function, on a compact metric space are achieved. So theorem, we have the following theorem. Okay, let f be defined on M metric space with real values, be continuous. So we assume it is continuous. Let K be a subset of M, which is compact. Okay, then there exists x0 and x1 in K such that for any x in K, f of x is between f of x0 and f of x1. So in other words, f of x0 is the minimum of f of x0 is the minimum of f of x belongs to k, and f of x1 is the maximum of f of x when x belongs to k. This is very interesting. In other words, we can we are bounded. So here, let me just go to the proof. Okay, proof. Since f of x is continuous, then f of k is compact subset of R. And we know that the compact subset of R are the closed bounded subset. Okay, exactly. Then f of k is closed and bounded. So in particular, the infimum of f of x when x belongs to k and supremum of f of x when x belongs to k exists. So next, we want to prove that in fact this infimum and supremum are minimum and maximum. Let me just prove it for the infimum. Okay, set m equal the inf of f of x when x belongs to k. Okay, then it is easy to show that there exists a sequence xn in k such that f of xn goes to m as n goes to infinity. Now, since k is compact, we are in metric space now. Since k is compact, there exists a subsequence xnk of xn which converges in k. In other words, a limit of xn equal x0 belongs to k when nk goes to infinity. Okay? So since f is continuous everywhere, it is also continuous at x0. So we must have a limit of f of x and k equal f of x0 when nk goes to infinity. And since f of x and k is a subsequence of xn, f of xn, then limit of f x and k is also equal to m, okay, equal to f of x0. So we found a point in k that achieves the infimum. Therefore, f of x0 is equal to the infimum, and because x0 belongs to k, in this case it is a minimum. It becomes a minimum x. Okay, similar proof will give us the supremum being the maximum. An application of this beautiful theorem is as follows. The next application: let f goes from m into R, defined by f of x equal the distance from x to a, where a is a fixed point in M. Okay, it's very easy to see that f is continuous since we have absolute value of the distance from x to a minus dy to a is less or equal than the distance from x to y. So in this case, we take delta equal to epsilon in the definition of continuity at any point. So it's independent of the point here. Of course, this inequality here, we get it from the triangle inequality. That's how we can get this one. So f is continuous everywhere. So if now we take let k be compact subset of M, then the distance, so then there exists x0 in k, okay, such that the distance from A to x0 is equal to the infimum of the distance from A to x belongs to K, which we defined before as the distance from A to the subset K. So the distance from a point to a set, if the set is compact, is achieved at certain point x0. Next, we continue our discussion on continuous functions defined on a compact metric space, and the next result is really a beautiful one. So if we go back to the definition of continuity at certain point, we see that for every epsilon there exists delta. That delta here depends on the point where we are studying the continuity and the function itself. What happened in a compact metric space will show that in fact the delta is independent of the point and only depends on epsilon and the function. Indeed, we have the following result. Theorem. Let F defined on a compact subset of a metric space N be continuous, where K is compact. Okay? Then for any epsilon there exists delta positive such that for any xy in K, the distance from x to y less than delta implies the distance from f of x, f of y less than epsilon. So as you can see, the delta here is independent of the point where the continuity was considered. Okay? Proof, same as in the real line. Okay? We know that f is continuous everywhere, so since f is continuous at any point in K, because it's continuous everywhere, so it's at any point in K, then we know that for any A in K, there exists delta of A positive such that for any x in K, the distance from x to A less than delta of A implies the distance from f of x to f of A less than epsilon over 2. Of course, the epsilon over 2 was chosen only for the proof at the end. It will look exactly what we wanted, meaning the epsilon that we are looking for here instead of having 2 epsilon. Then we know that K, obviously, K will be including the union of all the open balls centered in A with radius delta of A over 2. So now K is compact. Since K is compact, there exists A1, A2, etc. AN in K such that K is in the union of all these open balls AI delta of AI over 2 I between 1 and n. And now take delta to be the minimum of these delta i's over 2, and since they are finite, it sees one of them, and therefore delta is positive. Now, let xy in K such that the distance from x to y is less than delta. Okay, so first there exists an I0 such that x belongs to that open ball delta of AI0 over 2, and we claim, if everything is well done, we claim that y belongs to the open ball centered but without d over 2. Indeed, we have the distance from AI0 to y is less or equal from the triangle inequality to x plus the distance from x to y, which is less than delta of AI0 over 2 plus delta. But delta is less than delta of AI0 over 2, which gives me delta of AI0. So our claim is correct. And now we use the continuity at AI0. So we know now, so we have, by definition of the delta A's, we have rho of f of x f of AI0 less than epsilon over 2, and rho of f of y f of AI0 less than epsilon over 2. The triangle inequality then implies that rho of f of x f of y less than epsilon over 2 plus epsilon over 2, which is epsilon. So again, as you see, we were able to find a delta here, which is this delta here is independent of the point. It only depends on epsilon and the function itself, such that every time x and y are close up to delta, then f of x and f of y are close up to epsilon. This property here that we proved in the compact metric spaces is a new property, which is we introduce the following definition. Okay, so let f goes from M into N. M and N are two metric spaces. We say that f is uniformly continuous if and only if for every epsilon there exists delta positive such that for any x and y in M, the distance from x to y less than delta implies the distance from f of x to f of y less than epsilon. In other words, what we just proved is that continuous functions defined on a compact set are uniformly continuous. Clearly, it is obvious that uniform continuity implies continuity. In general, these two concepts are not equivalent. For example, there are easy examples on the real line that students can easily come up with where these two concepts are not equivalent. Again, they are equivalent only on compact sets. Another interesting example of interesting example of uniformly continuous functions are what we call Lipschitzian mappings or Lipschitzian functions. So, first let us give a definition. F defined from F to N is said to be Lipschitz if and only if there exists a constant L positive such that for any x and y in M, the distance of f of x to f of y is less than L, the distance from x, y. There is a control between the distance of the images and the distance of the pre-images. So this is the definition. The smallest constant L is called the smallest constant L is called the Lipschitz constant of F. And usually we use the notation, okay, for this smallest constant is given by lip of F. So let's it's easy to see that if we take assume F is Lipschitz with L, the constant of Lipschitz, positive as a constant of Lipschitz, then we may take delta equal epsilon over L to prove that F is uniformly continuous. Just to clear the air here, some people will believe that only Lipschitzian mappings are uniformly continuous, and the answer is no. So, for example, if we take F, which is defined from R to R, x gives me x squared, then F is Lipschitzian on AB for any closed interval, but F is not Lipschitz on R. In other words, this example gives you a function that is Lipschitz on a smaller set, but not on the bigger set. So this is also some of the properties. And if we take G from 0, 1 into R defined by square root of x, then G is continuous. So it is uniformly continuous because 0, 1 is compact, but G is not Lipschitz. This is something that the students can easily do. Next, we look at the set of all continuous functions defined on two metric spaces, and this is maybe the time. So first let me introduce some notation. So let xd and n y row be two metric spaces. Set C of x to y to be the set of all continuous functions from x into y. And what's interesting is that we want to define a distance on this set, which we will do the problem is that these functions may not be bounded. It's enough to take, for example, from R to R, and you look at all the continuous functions. These functions, some of them may not be, like x squared, may not be bounded. And so what we'll do, we can restrict ourselves. But before we do that, I need to introduce a new definition. And then, of course, we'll restrict ourselves to bounded continuous functions. So before, let f be a family, okay, of continuous functions from x to y. So we'll say, we will say f is equicontinuous at a point A in X if and only if for every epsilon, okay, for every X in X, there exists delta, which depends on A, and the whole family, of course, such that for every X in X, the distance from X to A less than delta implies the distance from f of x to f of a less than epsilon for any f in f. So in other words, the delta is independent of the individual element in the capital F. And we'll say, of course, we will say f is equicontinuous everywhere if it's equicontinuous at any point. Okay? So this is the local definition, and then we have the global definition. Also, we say f is uniformly equicontinuous. Equicontinuous if and only if for every epsilon there exists delta, but this time is independent of the point A, such that for every x and y in x with distance from x to y less than delta, then the distance from f of x to f of y is less than epsilon for any f in f. These two concepts of equicontinuous and uniformly equicontinuous were introduced by two Italian mathematicians more than 150 years ago, Ascoli and Arcera. And in order for us to state their beautiful results, we will need the following. So as I said earlier, we need to look at C of xy as a metric space. So what would be the distance between two functions? And in order to do that, so we're going to introduce another subset of C of xy. So consider C B of xy, which is the set of all bounded functions in C of xy. In other words, bounded and continuous from x to y. Okay. In particular, if K is compact, then we can drop CB. CB of K to Y is exactly C of K to Y, because any continuous function defined on a compact set will be bounded. And on CB, so let's go back to CB of xy, or we can define the distance. In other words, on CB of xy, we can introduce the new distance, d infinity between two elements, to be the sup of rho of f of x to g of x. X belongs to x. Okay, so this distance here, I mean, this number is only finite if we are on bounded functions. Otherwise, if they are not bounded, this number may become infinite. This, in fact, function defines a distance. It's obvious. Defines a distance on CB of xy. So in other words, we are here in front of CB of xy with d infinity is a metric space. And what's interesting is that if y is complete, then this one here, CB of xy d infinity, is also complete. Since in the previous web notes we never gave a proof of the completeness of a metric, so let us here show, it's a beautiful proof which shows you how to use in a complex or complicated metric space, how to use the definitions of Cauchy and conversions and so on. So let me, in this case, do the detailed proof of this fact. So let Fn be a Cauchy sequence in CB of xy. And we want to prove that Fn converges to an element in CB of xy. So first of all, what does that mean? For every epsilon, there exists n0 such that for every n greater than n0, for every m greater than n0, d infinity of Fn to Fm is less than epsilon. Obviously, fix x in x, we have the distance from Fn of x to Fm of x is less or equal to d infinity of Fn to Fm. So the sequence Fn of x in y is Cauchy. And this is where we need the completeness of y. Since y is complete, okay, limit of Fn of x when n goes to infinity equals to f of x exists. So pointwise, we do have a limit. Okay, so pointwise, the sequence of functions do have a pointwise limit. What we need to prove now is, number one, they do converge the fn's to this function f for the d infinity distance, and number two, that f belongs to CB of xy. So again, we have for any so we need to prove now that f of x is continuous. Let's go back to the property. So let epsilon be positive. There exists n0 greater than 1, such that for every n and m greater than n0, the distance between fn to fm is less than epsilon over 3. I changed it a little bit just so in the proof I can get epsilon instead of epsilon, 3 epsilon. Okay? So next, fix n0. So fix n greater than n0, and x in x. Then for any m greater than n0, we have rho of fn of x to fm of x less than epsilon over 3. We used already this fact before, and now let m goes to infinity. We get rho of fn of x to f of x less than epsilon over 3. Okay, so keep in mind that epsilon here, n0 is independent of the point. Okay, so in particular, the soup. So soup of rho of fn of x to f of x, x belongs to x, is less than epsilon over 3. Okay, so in other words, we have d infinity of fn to f is less than epsilon over 3. So right there we can see that f is bounded. Okay, this clearly implies f is bounded. Okay, I mean, it's just because you can use triangular inequality and use the boundedness of fn with this inequality to show that f is bounded. Okay, so for example, this is just for the sake of completeness to do it. Okay, let x and y in x, we have the distance from f of x to f of y, to show that it's bounded, is less or equal rho of f of x, fn of x, plus rho of fn of x, fn of y, plus rho of fn of y plus, f of y. So here we will see that this is less than epsilon over 3 plus the supremum of rho of fn of x, fn of y, x and y in x, plus epsilon over 3. So you see here that supremum of rho of f of x, f of y, when x and y are in x, is finite. So it is bounded. So fn is bounded. Okay, so next we want to show that f is continuous, okay, at any point. So let a belongs to x, okay, and we need to prove, let us prove that f is continuous at a. Okay, so we're going to use the continuity of fn. So since, remember, we fixed n, since fn is continuous at a, there exists delta such that for every x in x, the distance from x to a less than delta imply that the distance from fn of x to f of a is less than epsilon over 3. So again, just to convince you, We know that n depends on epsilon because we found n0 from the Cauchy sequence, the Cauchy definition of Fn. So the n here depends on n0, depends on epsilon, okay? And therefore the delta, which depends on Fn, also depends on epsilon, okay? So we have, okay, for every x in x such that the distance from x to a less than delta, okay, then rho of f of x, f of a is less or equal from the triangle inequality f of x, fn of x plus rho of fn of x, f of a plus rho of f n here, sorry, fn of a to f of a. So again, each one of them is less than epsilon over 3, which gives us epsilon. So this shows us that f is continuous. So bounded, so f, in fact, belongs to CB of xy. And if you go back here, we showed that for n greater than n0, d rho, d infinity, sorry, of fn to f is less than epsilon right here. So it's less than epsilon over 3, which is less than epsilon. So this, of course, clearly implies that limit of the sequence fn is equal to f. So any Cauchy sequence in CB of xy is convergent, and the limit exists and belongs to CB of xy. So for CB of xy with this distance is complete. So before we state the Ascoli-Arzela theorem, let us first give a little topological property. Okay, so recall that A is said to be relatively compact. Okay, if and only if the closure is compact. Okay, so now we are ready for the theorem, beautiful theorem of Ascoli-Arzela. Let K be compact and consider C of K Y as before. So keep in mind we don't need the B because BK is compact, okay? Where Y is assumed to be complete metric space. Okay, so we know that in this case the CKY is complete metric space for the D infinity distance. Then we have for any family of functions from C of K to Y, sorry, not X, from K to Y, F is relatively compact if and only if F is equicontinuous everywhere epsilon k, and for any x in k, f of x, which is the images, the set of f of x, x, is relatively compact in Y. So what's interesting here is really amazing, beautiful theorem. What the theorem says, in fact, is that this uniform relative compactness, okay, in fact, is a pointwise. You can check it pointwise instead of checking it uniformly in the space of continuous functions. You can only look at it as pointwise in the metric space. This is what you can take it from pointwise to the uniform behavior. So let us give the proof. Interesting proof, very rich. So here, first, let us assume that F is relatively compact. Since, as we have seen, K, Y is complete, okay, then F is totally bounded. This is totally bounded. So for any epsilon positive, there exists F1, F2, Fn in F, such that for any F in F, there exists I, such that the distance from F to Fi is less than epsilon. Okay, so in particular for any x in K, we have rho of f of x to Fi of x less than epsilon. Okay, or f of x is in the union of the open balls centered in Fi of x with radius epsilon, I between 1 and n. So in other words, f of x is totally bounded. Totally bounded in Y. Okay, since Y is complete, since Y is complete, then f of x closure is complete and totally bounded. Hence, f of x bar is compact, or f of x is relatively compact. Okay, so one part is done. Now assume that the converse, let us prove the converse now. I think we have, I'm sorry, before I jump into the converse, the theorem is equicontinuous. If and only f is equicontinuous everywhere, and f of x is relatively compact. So we showed that f of x is relatively compact, but we did not show that f is equicontinuous. So before, we are not completely done with this. So let us next prove prove that f is equicontinuous. Let A belongs to K. Let epsilon be positive. So now we are going to use that f of f is totally bounded, since f is totally bounded. There exists f1 fn in f such that for any f in f there exists I such that the distance from f to fi is less than epsilon over 3. Okay, now let's take since each fi is continuous at A, is continuous, there exists delta I positive such that for every x in K, the distance from x to A less than delta I will imply rho of f of x to f of I of A less than epsilon over 3. Okay? So now let any f in f, there exists I0 in 1 to n such that d infinity from f to fi0 is less than epsilon over 3. Okay, so now we have for any x set delta equal the minimum of the delta i's. Okay, then keep in mind the delta is independent of f. It only depends on the fi's. So then for any x in K such that the distance from x to A less than delta, then d of xa will be less than delta I for any I. So for that f, for this f here, there exists an I0. So we have rho. Okay, we have rho of f of x, f of A, less or equal rho of f of x, fi0 of x plus rho of fi0 of x, fi0 of A plus rho fi0 of A f of A. So this one here is less than epsilon over 3. This one here is less than epsilon over 3. And this one here is less than epsilon over 3 because we're using the definition of delta. dxa is less than delta, which is less than delta I0. So we get this is less than epsilon over 3, epsilon over 3, epsilon over 3, which gives us epsilon. So rho of fx to fa is less than epsilon, which shows us independently of f that the family F is equicontinuous. And this, of course, finishes the proof that if we are relatively compact, if F is relatively compact, then F is equicontinuous and f of x is relatively compact in Y. Next, we prove the converse. Now we're ready to prove the converse. Next, we prove the converse. Okay? So, assume f is equicontinuous. And f of x is relatively compact in Y for any x in K. Okay? So we need to prove that f is relatively compact in C of xy. Let us prove that f is relatively compact in C of ky. Since C of ky is complete, we only need to prove that f is in fact totally bounded. Okay, so since K is compact, okay, then we can use the same idea of the proof where we showed that continuity implies uniform continuity to show that in fact f is uniformly equicontinuous. Same proof, exactly the same. Uniformly equicontinuous. So for any epsilon, for any epsilon positive, there exists delta such that for any x and y in K, the distance of x to y less than delta implies rho of f of x, f of y is less than epsilon over 4 for any f in the family. So that's the uniform equicontinuity. Okay? Now, since K is in the union of open balls, okay, and K is compact, there exist x1, x2, xn in K such that K is in the union of the open balls xa delta I between 1 and n. Okay. Okay. Our assumption, we know that f of xi is relatively compact in Y, but since Y is complete, it's the same as totally bounded. So for any I, okay, f of xi is totally bounded in Y. Okay, and therefore there exists, so there exists yi1, yi2, yi ny such that f of xi is in the union of the open balls yi little k between 1 and ni, with radius epsilon over 4. Epsilon over 4 because at the end, instead of having epsilon, we'll get 4 epsilon, and that's why we're dividing right here by 4. So it's not okay. And before also, when we considered right here, when we said uniform, here, right here, also we used epsilon over 4, again for the same reason that at the end of the proof we'll find 4 epsilon, and instead, so we divide by 4 just to make sure that at the end we'll find epsilon instead of 4 epsilon. So now, clearly from here we get that the union of f of xi's, okay, is going to be included in the unions of all these open balls, and if I put them all together, all these balls are equal to, let's say, centered at zi's. I mean, let's not use I. Let's use j epsilon over 4, where j is between 1 and some numbers m. Okay, so we have finitely many open balls centered at certain points. If they are the same centers, put them together. If not, count them. So we have these zj's are all these centers. Okay, so but there are finitely many of them. Now let gamma to be mappings, okay, from 1 to n into 1 to m. So we know these are just mappings on the integers, so gamma is finite. Gamma is finite. And we know for any lambda in gamma, if I set f lambda to be f in f, such that the sup of row of f of xi to z of lambda I less than epsilon over 4, and I is between 1 and n, then we have, okay, we have f, which is in the union of f lambda when lambda belongs to gamma. So this is a finite partition of f. And what's interesting is to notice that the diameter of f lambda is less than epsilon over epsilon. So let's look at it. Okay, so here let us prove this. Let f and g belongs to f lambda. So here, for every x in k, there exists an I in 1 to n, such that the distance from x to xi is less than delta. Okay, and so we have rho of f of x g of x is less or equal rho of f of x to f of xi plus rho f of xi to z of lambda I plus rho of g of xi z lambda I plus rho of g of xi g of x. And every piece is less than epsilon over 4, which gives us epsilon. So the diameter, so since sup of rho of f of x, g of x, x belongs to k, is less or equal than epsilon. Okay, so here the diameter of f lambda is going to be less or equal than epsilon. Okay, but in fact what we're going to say, so let to see balls, because we're not totally bounded, we use the definition of balls in the definition of totally bounded, so that's fine. We take f lambda, pick, so let f lambda be in f lambda, and then it's obvious f lambda is included in the ball centered in f lambda with radius epsilon. So this way f is included in the union of all the balls f lambda epsilon over lambda belongs to lambda, and this shows that f is totally bounded. Okay, so this completes the proof of the theorem of Ascoli and Arzela. Remark: we have a special case. Since K subset of Rn is compact, if and only if K is closed and bounded. So in Rn, we know that you just need to be bounded. You don't need to be totally bounded. So in this case, we have the following. We have the following corollary. Corollary as a direct result of the theorem we just said. So let K be a compact subset, compact metric space, and then F subset of CK Rn. So here Y is Rn. So is relatively compact if and only if F is equicontinuous, which is exactly what we had in the theorem of Ascoli. And now we have f of x, which is relatively compact. So what we are going to assume here is that you have some kind of boundedness and uniformly bounded, meaning there exists a positive number m such that for any x in K, f of x is bounded and the diameter of f of x is less or equal than n. So you see, the fact that f of x is bounded, then we have the relative compactness that we're looking for. Okay. So this, of course, is a corollary of the theorem of Ascoli and Arcela. Let us finish this web note by giving an example. Let Fn defined on the interval 0, 1 into R be continuous. So we have a sequence of continuous functions such that the sequence Fn are uniformly bounded on 0, 1. So this is the condition here that we're assuming. Okay. Moreover, and we assume that the Fn's are all have a derivative f prime n are uniformly bounded on 0, 1 open. Okay. So claim Fn has a subsequence which converges uniformly. This is a wonderful application of the Ascoli-Arcela theorem. Okay? So first of all, note that since what does that mean? First of all, what does that mean to be the sequence to be uniformly bounded of f prime of n? It means that there exists. Okay, so f prime n are uniformly bounded if and only if there exists a positive constant such that for every x inside 0, 1, fn prime of x absolute value is less than n. Okay, so the mean value theorem, will imply that for every x and y in 0, 1, okay, absolute value fn of x minus fn of y is less or equal than mx minus y. And this, of course, will imply, see, we have like a family of uniformly Lipschitzian mappings with all the same constant of Lipschitz m. And therefore, this will imply that the sequence Fn is uniformly equicontinuous. I mean, the delta will be epsilon over m, continuous. And as we said, since Fn are uniformly bounded, then for any x in 0, 1, the sequence Fn of x is bounded. So Fn of x is relatively compact. So now we can use the corollary, because 0, 1 is compact, in C 0, 1 R. Okay, with the uniform distance, with d infinity, to see that Fn has a subsequence, a convergent subsequence. Obviously, the convergence is the uniform convergence defined by d infinity. So this lecture was a long lecture, but this will prepare us for what's coming after that when we consider mappings and operators defined between normed vector spaces. Hope you enjoyed this lecture, and thank you very much.